Good afternoon, everyone. Am I audible? Please mention in the chat box whether I am audible or not. Okay. Okay, so only 12 students are present. Where are the others? Okay, so last class we have done about the activated sludge process. Yes, we have completed the activated sludge process. We have done the advantages and disadvantages of your activated sludge plant also, I guess. Yes, we have done this one also. Okay, so today, with today's class, we will be finishing up your treatment plant, okay? The treatment, the whole process, the whole treatment chapter, we will be ending up today, okay? So before that, I would like to show you one video, and after that, we will be doing two numericals related to your trickling filter, okay? Trickling filter plant, we will do two numericals. So, first, that day we had discussed about the activated sludge process and the trickling filter process differences and like the advantages and disadvantages of those things. And today, related to that, I would like to show you one video so that it would be more clear to you the both the trickling filter and activated sludge process as a together, okay, as a whole together process, which one is better and what are the advantages of your trickling filter process. So that video I would like to show you today. So after that we will be solving two numericals, okay.
Trickling filters, also known as biofilters, are normally a fixed-bed biological reactor operating in aerobic conditions. In the filter, microorganisms are attached to the inter-packaging material, which was composed of rocks or gravel in the past and is nowadays a wide range of plastic film media. Film media support is placed on the tank bottom, with wide openings that allow a good air and water mixing. Microorganisms on the film media surface work on the removal of soluble organic matter from the settled sewage that is sprayed over the bed surface through a rotary distributor and is treated as it trickles through the fixed bed, navigating through layers of microorganism. The layers remove pollutants by both absorption and absorption-removing species like nitrite, nitrate, and others. Removal rates can reach up to 95%. In order to avoid clogging, a primary sedimentation process precedes the trickling filter. Also, the design of the rotary distributor has a high impact on the risk of clogging. The rotation velocity of the rotary distributor can be changed by either adjusting the incoming water flow or by using an electrical motor. As smaller the rotation velocity, as higher the water volume per square foot, and as bigger is the flushing effect. In time, the biofilm thickens and detaches into the liquid flow, forming the secondary sludge. Trickling filters are normally followed by clarifier or sedimentation tanks. The sludge collected is treated for reuse or prior to disposal. Among the main advantages of this system, it is important to highlight the resistant to shock loadings, high efficiency for ammonia oxidization, small land area required, final effluent is effectively stabilized. The system is self-cleaning, operating with low maintenance requirements. Operational costs are low since wear and tear are reduced due to limited use of mechanical equipment. Furthermore, in comparison with similar methods such as activated sludge, trickling filters are significantly more cost-effective as they don't require artificial aeration and have a smaller demand for operational space, resulting in cost reduction. Thanks for watching, and if you like our 3-minute tutorials, please subscribe and don't forget to give a thumbs up.
Okay, so you have seen the advantages and disadvantages, okay? So it's clearly explained in the video also. Okay, now coming back, let us solve like two numericals, okay? Related to your trickling filter. Okay, so before solving the numerical, first let us go through the design considerations, or you can say, or like the design considerations of the trickling filter, okay? So, okay, okay, you see from the first what's written here. Let me change the color. Okay. So it's written like the design of the trickling filter primarily involves the design of the dia of the circular filter tank and its depth. So if like in the question it's given to design the trickling filter, so what it involves the design of what? The dia of the circular filter tank, okay, and its depth. So the design of the rotary distributors and under drainage system is also involved in the filter design. So you have seen that trickling filter. I have shown you the video also, and I have shown you the cross-sectional diagram also. So you need to design the rotary distributors also and under drainage system also. Okay, but that makes the numerical a bit long. The design of trickling filter numerical is a bit long. So the design of the filter size is based upon the values of the filter loadings adopted for a design. This loading on a filter can be expressed in two ways. So you have to design the filter size also, and that depends upon what? That depends on the values of the filter loadings, how much of loading is you have applied to the filter. Okay, so that depends on the filter loadings, and also the loading of the filter, it can be expressed in two ways. Okay, so what are they? Let us see. Number one is your, like, by the quantity of sewage applied per unit of surface area of the filter per day. So how much of quantity of sewage is applied on the surface area of the filter, okay, per unit surface area of the filter on a particular day, okay, per day. So that is known as your hydraulic loading rate. Okay, so what is a hydraulic loading rate? It is the quantity of sewage that is applied per unit surface area of the filter per day. Okay, so that is your hydraulic loading rate, and it is expressed in, what is the unit of hydraulic loading rate? It is your million liters per hectare per day. Okay, it is expressed in million liters per hectare per day. Clear? So now, million liters per hectare per day. Okay, so the value of the hydraulic loading for conventional trickling filters. So we have done two types of trickling filters. What are those? One is your conventional trickling filter, and the other one was your high rate trickling filter. Okay, so the conventional trickling filter, what is the value of the hydraulic loading? It is, okay, it is between your, it may vary between your 22 to 44 million liters per hectare per day. Okay, and the hydraulic loading, it can be increased. Okay, it can be increased. So the normal value is between like 22 to 44, and the normally it is taken to be, suppose you have to take something, so it is between your 28. Okay, you can consider 28 million liters per hectare per day, and that value, it can be increased about to about how much, 110 to 330 million liters per hectare per day in case of your high rate trickling filters. Okay, for conventional it is 22 to 44, and for your high rate trickling filters it is 110 to 330 million liters per hectare per day. Clear? So there it is between 22 to 44, and then normally you can take 28, and here for high rate trickling filter it is between 110 to 330, and normally you can take it between you can take the value of 220, but this depends upon you. Okay, whatever value you take. So now number two is your one was your hydraulic loading rate, and the second one is your organic loading rate. Okay, so what is the organic loading rate? It is like by the mass of BOD per unit volume of the filtering media. Okay, you see, by the mass of BOD per unit volume of the filtering media per day. So this is your organic loading rate. These are the two kinds of loadings, filter loadings, that you will find in trickling filter. So, and this organic loading rate, it is also expressed in kg of what, BOD 5 per hectare meter of the filter media per day. Okay, so what is the value of the organic loading for conventional filters? It is between your 900 to 2200 kg of BOD 5 per hectare meter. And what about the high rate trickling filter? It is about it is between 6000 to 18,000 kg of BOD 5 per hectare meter in high rate trickling filters. Okay, like for solving the numericals, you have to remember the loading rates. Okay, for conventional and for high rate trickling filters, what is the hydraulic loading rate, is what is the variation of the hydraulic loading rate, and also the organic loading rate you have to remember. Okay, so next is your it's written here that with an assumed value of organic loading as between 900 to 2200 kg per hectare meter, we can find out the total volume of the required filter. So after you like assume the value of the organic loading, so after that you can find out the value of what the total volume of the required filter, whatever the filter size you are going to find out. So you can find out the total volume of the required filter. How you will find out? By dividing the total BOD5 of the sewage entering the filter by the assumed value of the organic loading. Okay, so it is like BOD5 divided by your organic loading. Okay, the value of the organic loading. So the organic loading, it will decide the volume of the filter. Okay, so why you are finding the organic loading? So that you can find out the volume of the filter. Clear? So the hydraulic loading, on the other hand, it gives us the area of the filter. So why we are finding the hydraulic loading? Because we need to find out the area of the filter. Okay, and the organic loading, we are finding the organic loading because we need to find out the volume of the filter. You remember this difference? Okay, hydraulic loading is to find out the area of the filter, and organic loading is to find out the volume of the filter. Clear? So here, when when the total sewage volume entering the filter per media is divided by the hydraulic loading. So like the formula is similar. Okay, formula is similar, but one is to find out the volume and the other one is to find out the area. So next, but after you know the volume and the area of the cylindrical filter, so we can easily find out the diameter and the depth of the filter. Okay, after you find out the volume and area of the filter, we can find out the diameter and the depth of the filter. So it is again here you see it is mentioned here. It may also be mentioned here that the filter diameter and depth, it is designed for average value of sewage flow. Clear? So the filter diameter and the depth of the filter, okay, it is designed for what? Average value of the sewage flow. Suppose in the question average value will be given, so you have to multiply your the filter dia, you have to get the filter dia, you have to multiply with the average value of the sewage flow. Clear? Then after that, the rotary diameter distributors. So I have shown you in the video the rotary distributors. I think you have seen the four arms like this. Okay, from where the the sewage was coming out. So that was your rotary distributors and the under drainage system. So below the below the treatment, below that net type thing, no, there is a under drainage systems there, and they are connected pipelines. Okay, the rotary distributors, under drainage system, and other connected pipelines, etc., are, however, designed for peak flow and, of course, checked for the average flow. So here it is said here that the filter dia and the depth is designed for your average sewage flow, and the rotary distributors and under drainage system and the other connected pipelines, they are designed for what? Peak flow. And after you find you find out the peak flow and average flow, so after that you need to check also whether it is permissible or not. Okay, so now the rotary distributors are available indigenously only up to 60 meter in length. Okay, so the rotary distributors, it is available only up to 60 meter in length, and it is desirable to keep the dia of the filter tank up to a maximum of 60 meter. So you need to keep the diameter to a maximum of what? 60 meter. Okay, so now with all this, again you have to find out the efficiency. Okay, you need to find out the efficiency of the filter. So how will you find out the efficiency? So this is the formula. Okay, this is the formula. Efficiency is always in percentage, that one you everyone knows. So the formula is 100 by 1 plus 0.0044 root over u. So what is eta? Eta is your efficiency of the filter and its secondary clarifier in terms of percentage of applied BOD removed. So it is in simple, it is efficiency. And what is U? It is your organic loading in kg per hectare meter per day applied to the filter. Okay, so U is your organic loading. So you will get the value of organic loading in the first step only. So after that, you have to just put the organic loading value and you can find out the what is the efficiency of your trickling filter. Clear? So now we will design one numerical trickling filter we will design. So the question is like design suitable dimensions of a circular trickling filter units for treating 5 million liters of sewage per day. The BOD of sewage is 150 milligram per liter. So one part of the question is to find out not to find out, sorry, to design the circular trickling filter. Okay, to design a circular trickling filter whose like it is given it is used for treating 5 million liters of sewage per day, and the BOD of the sewage it is also given as your 150 milligram per liter. So the other part of the question is to design the suitable dimensions for its rotary distribution system as well as the under drainage system. Okay, so there is a two-part question. So here in the exam, if it comes like only the first part, no need to design the second part like the rotary distribution system, you no need to design. Okay, so and if the second part comes, then you have to design the whole problem from the dimensions to the rotary distribution system. You have to design the whole problem. Okay, so let us see the solution, how it is solved. So first, since here it is given that 5 million liters of sewage is treated per day and the BOD of the sewage is also given as your 150 milligram per liter. So you find out the total BOD. Okay, total BOD present in the sewage to be treated per day. So how you just multiply both. Okay, so if you multiply both the values, you will get the total BOD that is present in the sewage and that is to be treated per day. Okay, so after converting to kg, we are getting the value of 750 kilogram. Okay, after converting to kg, it was in milligram, so they have converted it to kg, so it is your 750 kg. Okay, so now you have to like assume the organic loading. Now you have to find out the volume. Okay, you have to find out the volume of the filtering media. So in order to find out the volume of the filtering media, so what you need to assume? You need to assume the organic loading. Okay, just now we have studied. So organic loading, we have learned that it was between your 900 to 2200 kg per hectare meter per day. So you assume a medium value. So they have assumed it to be 1500 kg hectare meter per day. Okay, so they have assumed the organic loading value as your 1500 kg per hectare meter per day. So now you find out the volume. So we have already learned that to find out the organic loading is used to find out the volume of the filtering media. So now you find out the volume. So volume, how will you find out? It is like the total BOD divided by your organic loading. Okay, organic loading, so you it is in hectare meter. So if you convert hectare meter to meter cube or like to meter square, okay, you convert this hectare to meter square and you will get it 5000 meter cube. Meter cube, why? Because it will be converted to meter square and this is meter, so both will combine and it will be meter cube. Okay, so now after finding the volume of the filtering media, you find out the effective depth of the filter. Okay. So now you find out the effective depth of your filter. Okay. So you have to assume the effective depth of the filter and that is your 2 meter. For this problem, they are for the trickling filter, they are assuming the effective depth of the filter as your 2 meter. Okay. So now as soon as you get the effective depth of a filter, now you can find out the surface area. Okay, so you have to find out the surface area. So there are two units, okay, and you have two filters are there. So now you have to find out the filter of one, okay, the surface area of one filter. So how will you find out? You have to divide it by two, okay. So you see here, sorry, this is the effective depth of the filter. This is 2 meters. So this is the surface area, okay. Surface area formula, it is your 5,000, like the volume divided by the effective depth, okay. This is your volume divided by your effective depth. It comes up to be 2,500 meters square. Clear? So now you have to again like assume a trickling filter of diameter 40 meter, okay. This one also you have to assume, like use a circular trickling filter of dia 40 meter. We have the number of units required, so we need to find out the number of units that is required for your trickling filter, okay. So you have assumed the effective depth also and organic loading rate also, and now you are assuming the diameter also, okay. So you need to remember this, like 40 meter they are assuming the diameter. Okay, so now after assuming this diameter as 40 meters, so now you have to find out the number of units. So that will be your total area required divided by area of one unit. So total area we have already got it to be 2,500 meters square. Okay, so it's 2,500 divided by what is the area of one unit? It will be, since it's a circular trickling filter, so it will be pi by 4 divided by 40 square. Okay, pi by 4 d square formula. So it will come to be like two numbers. Okay, so two numbers of filter units you are using. Okay, you got two number of units of filter. Okay, so now you have to check for the hydraulic loading. So we have done the organic loading part. So now you have to find out the hydraulic loading. Okay, so how will you find out the hydraulic loading? You see here, it's written here that the surface area of the filter bed required, it can also be worked out by how? By assuming the hydraulic loading. Okay, so hydraulic loading we have studied before that it should be between 22 to 44 million liter hectare per day. Okay, so it should be between 22 to 44 million liter hectare per day. So you assume one like medium value. So it's written there that normally it is taken as to be 25 million liters. So you take to be 25 million liters. Okay, the hydraulic loading. So now you find out the surface area, because again we have studied that for why we find out the hydraulic loading. We find out the hydraulic loading to find out the area, okay, area of the filter. So what is you find out the surface area of formula. It is like total sewage to be treated per day divided by your hydraulic loading per day. That one also we already got. Okay, so it will be like here it's total sewage is it's given in the question it to be 5 million liter. Okay, and what is the hydraulic loading? It is 25 million liter per hectare. Okay, so it's divided by like 5 by 25. It will come up to be it's in hectares, so they have converted it to a meter square. Okay, so how will you convert? So it's 1 meter, 1 hectare is equal to 10,000 meters square. Okay, so they have converted it to meter square and you got it to be 2,000 meters square. Okay, so the hydraulic loading part is done. So now you can write that the surface area chosen is 2,500 meters square, which is greater than 2,000 square meter and hence safe. That means actually the surface area, it should be in 2,000. Okay, it should be like greater than 2,000. It should not be below 2,000. So since here you got to 2,500 meters square, which is greater than 2,000 square meter, so it is, the design is safe. Okay, and finally the final line you can write as like you have to like two units you got. Okay, each of what we have assumed 40-meter diameter and 2-meter effective depth. So 2 meter is effective depth, and if you provide freeboard of 0.6, so the total overall depth you will get it to be 2.6 meter. Okay, so now, and one extra third unit also you can provide as a standby. Okay, later you can use it. Okay, so this is your first part of the numerical solved. Okay, so next is your the design of rotary distributors. So rotary distributors you have seen, and the rotary distributors, they are designed for what we have just studied. It is designed for your peak flow. Okay, so peak flow is your 2.25 times the average flow. Okay, so the peak flow, it is considered here as your 2.25 times the average flow. So if you find out the peak flow, if you find out the peak flow, this is your 2.25 times the average flow. What is the average flow? It is 5. So here they have multiplied it both, 11.25 million liter per day. So again they have converted it to cubic meter per second. So ultimately you will get it to be 0.13 meter cube per second. Okay, so now the flow, it is divided into two filter units, and therefore you have to divide this peak flow divided by 2. Since there are two filter units, you have to find out the flow through each unit. So how to find out the flow through each unit? You have to divide 0.13 divided by 2. You will get it to be 0.065 meter cube per second. Okay, next, it's quite a long numerical. Okay, so next you see, now you have to assume the velocity at peak flow. Okay, you have to assume the velocity. Why to assume the velocity? Because you need to find out the diameter of the central column of the rotary distributor. Okay, you have to find out the diameter, so you need to assume the velocity at peak flow. What is the velocity at peak flow? You have to, it is taken here to be 2 meter per second. Okay, 2 meter per second of velocity of flow is coming through the central column of the distributor. So now we have to find out the diameter of the central column. So how will we find out? It is like root over 0.065 divided by 2 into 1 by pi by 4. Okay, this is the diameter, this formula. Okay, so it's like 0.065 divided by 2 into 1 by pi by 4. Okay, so okay, so at 5 minutes the meeting will end. Okay, if it closes down, please join again. Okay, so you get it to be like 0.2 meter. Okay, so now the central column diameter, you got it to be 0.2 meter. So but we have to check the velocity through the column at average flow. So okay, you have taken the peak flow, but we have to also check for the diameter for the average flow. Okay, and it should not be less than 1 meter per second or so. Okay, it should not be less than 1 meter per second. So now you have to check the flow velocity for average flow, at average flow for through the central column. So now you have to find out the discharge through each unit at average flow. So how you will find out? It is like the total sewage flow divided by 2. Okay, 2, you will get it to be 2.5 million liter per day. Okay, so now you convert this 2.5 million liter per day to your meter cube per second. So you will get it to be 0.029 meter cube per second. Now you have to find out the velocity. So to find out the velocity, again your discharge q by pi by 4 d square. So here d is your 0.2. We have assumed 0.2 diameter, isn't it? So it is coming out to be 0.92. But it is already mentioned that the velocity for average flow, it should not be less than 1 meter per second. But here you can see it is 0.92. That means it is not safe. Okay, it is not safe, and again you have to assume another diameter. Okay, so slightly less diameter if we assume, like 0.2 we have assumed before. So now if we assume 0.19, so we have to again find out the velocity. Okay, so using 0.19 diameter, again if you find out the velocity, you will get it to be like 1.023 meter per second, which is slightly greater than 1 meter per second, and hence this is permissible and it is safe. Okay, so next, Next is your, like we have one table, okay, we have one chart, and there it is like the ratio between small d by capital D, small a by capital A. So those things were written, okay, but okay, so after this actually, okay, though I don't have the page after this. This numerical, it was finished here, okay. A little bit 2 3 lines were there, but I don't have the picture with me, the PDF with me right now. I forgot to click the photo, but next class I can provide you this numerical, okay. This is almost finished. This is almost finished. Just 1 2 3 line is permissible is there. So 2 3 lines were there, so I will provide you that one in the next class, okay. So this numerical is a bit long, and it's little bit not difficult, it's little bit of confusing. You have to remember the assuming things, you have to remember, then you can automatically you can solve the numerical, okay. So okay, let us end up today's class here. I was about to show you another numerical, but no time, so let me take your attendance. If it ends, then you quickly rejoin, okay? Roll number one,
Yes, ma'am.
roll number two,
Yes, ma'am.
three,
Present, ma'am.
four,
Present,
five.
ma'am.
Oh, four is
Ma'am.
present, okay.
Yes, ma'am.
Okay, five, six, seven, eight, nine,
Present, ma'am.
10, 11, 12,
Present, ma'am.
okay, 13, 14,
Present, ma'am.
14, 15, 16, 17, 18,
Yes,
9,
ma'am.
okay, 18, 19, 20, 21, 20 is present? Okay, okay, 21, 22,
Yes,
okay,
ma'am.
22, 23, 24,
Yes, ma'am.
okay, 25,
Present, ma'am.
26,
Yes, ma'am.
27, 26, okay, 27, 28, 29,